Thank you, Albert, for the very nice and concise introduction. This is the first time I come to India, and also, of course, the first time I come to Purdue. And I'm lucky to have a very nice weather today, roughly comparable to the weather in Bay Area where I'm currently living. But I know it's going to be cold tomorrow, actually. Hopefully not going to be snow, but I'm used to cold weather, actually, because I spent 5 years in New York City, you know. And to add to the contrast, actually, before I moved to New York City, I spent 8 years in a tropic and humid country called Singapore. I was there for 8 years. You only have one season throughout the year, summer. Okay, anyway, so let's back to business. So I'm going to talk about nonconvexity today. And as Elwer introduced.
One thing I'm going to do is how about the medium?
Okay.
Better maybe for everybody. And this chair's often yeah. Sorry.
It's fine. It's fine. Okay. I'm a postdoc in Stanford right now. Okay. So Euler believes that everything in the universe can be optimized. The truthness may be arguable. But anyway, the problem of finding global optimal for a given function has a history of at least 3 centuries old. And also, its development is actually attached to quite a number of big or giants in mathematics and physics, from Euler to Newton to modern heroes like Fourier, Cauchy, or Helmholtz. And if you look around, especially in applied science or engineering, you'll see a lot of problems where you can formulate the problem into mathematical optimization. Just to give you some idea, I take several brief examples from the areas that I happen to be working in. For example, in computer vision, whenever you want to construct street structure from a collection of images, you need to do some optimization. In signal processing, if you want to denoise a given signal, or if you want to design innovative sensing mechanism for say medical images, you need to do optimization. Of course, in machine learning, whenever you want to use your support vector machine to do classification, or if you want to do Bayesian inference. And in scientific imaging, if you want to image in minor scale object, normally you need to solve certain kind of inverse problem where, again, you face some optimization problem. And lastly, but not the least, the most remarkable one nowadays is the neural network, where basically you have a highly non-convex and sometimes even non-smooth operation problem. Okay. So over the past 50 years, people have loved this ball-shaped kind of function called convex functions. The nice thing about this kind of function is that all local means are global. Okay. And the development along this line is marked by 2 landmark events. The first is the invention of the interior point method around the 80s until 2000. So this achievement basically implies that most convex problems can be solved efficiently. Efficient here means polynomial time. And the second achievement is actually the invention of modeling language for convex programs, where by using modeling language, you can basically translate your convex formulation line by line into simple prototype language. And then you push the button and get some reasonable solution for your problem. And the development is so successful that, for quite a long time, people believe that the right intellectual division between tractable and intractable for numerical optimization is actually between convexity and nonconvexity. And this guy is a giant in convex analysis called Rockefeller. So we love convex optimization. What about non-convex problems? We kind of don't like it because if you pull out your mental picture about non-convex problems, you tend to think non-convex problems have this kind of global shape. Especially you have a lot of local means that are not global. So we have a lot of sparse local means. And actually, this sentiment is kind of backed by computer kind of computational theory, where it's known that not only finding the global mean for a non-convex problem is hard. Actually, computationally, try to find a local mean is hard. Okay. But unfortunately, or fortunately, many problems that we encounter are actually non-convex. We have to live with that, okay? They are non-convex. So how do we deal with that? Well, we know the theoretical difficulty, but in practice, what people do is that whenever they have some non-convex problem, they just pull out, simple algorithm they know. For example, gradient descent, which is first order method. Or if you are more, sophisticated, you can try second order method, some quasi-Newton method, BFGS, these kind of things. And often you are lucky and you can actually find some very high quality solutions to the problem you care. One remarkable example, again, is on deep learning nowadays, where, as we mentioned, we have a highly non-convex and actually also non-smooth problem often. And you just try stochastic gradient descent, plus some dirty tricks, I would say, because they are dirty because people haven't really understood them. But anyway, by doing this, you can actually get pretty remarkable performance in doing things like image classification, natural language generation, that kind of thing. So what happens here? How to bridge the gap between the theory and the practice? Especially the question that I try to address throughout this talk is that what kind of non-convex problem are easy? Okay, that's our central question in this talk. Before I try to offer some answer to that question, I will introduce a running application. So this application is called specifying transform learning. So the task is basically given some data Y. We are going to learn some transformation Q such that after I apply this transformation to the data, the representation becomes simple. Okay, maybe all these things are matrices. Then you can measure the simplest by counting the number of non-zeros in the final representation. Yes?
Is that what the zero means? Number
of non-zeros.
Okay, so it's a percentage of the total.
Yes, sparsity level, yes. And just to give some idea why we care this kind of problem, it finds a lot of applications in image signal processing and computer vision and other areas. So especially in image denoising, you can actually divide the image into patches and try to seek this kind of specifying transformation. And after you do the transformation, you throw out a small representation coefficient that most of the time actually corresponding to certain level of denoising to the image. And also, if you have a low resolution image and you want to recover some high resolution detail for the image, you can do some kind of transform learning. And you can even do some fancier things by cascading several levels of transformation, and which is actually a primitive form of deep learning. Okay, and you can use this for doing visual recognition. So I have to say that this problem is relevant to another problem called dictionary learning, which is formulated as a factorization problem. These two problems are equivalent in some cases, but in general, they are not equivalent, but they are relevant. I will focus on this version for this talk. And again, both of them find a lot of applications in image processing, computer vision. And actually, increasingly, they found powerful applications in computational imaging nowadays. And again, you can actually do cascading things, add in more nonlinearity and get, fancier. So this is our problem. And I'm going to restrict the problem even further. I'm going to restrict the transformation we are going to learn to be a orthogonal matrix. Okay? So this Q is orthogonal. After the transformation, I hope the matrix is sparse. One natural formulation for this problem is that I try to apply some vector to the matrix Y, and afterwards I get some sparse things. Of course, the natural question is that why don't you just put a matrix here? Okay, the reason is that putting a matrix is, going to make the problem challenging, and we'll see later that actually solving this vector variant actually solves the original problem. So if you look at this optimization problem, okay, the objective is fine. Okay, we have sparsity, and over the last decades, people know that whenever you have sparsity, you have some natural candidate for promoting sparsity. For example, you put L1 norm instead of L0. This constraint is really strange, because in optimization, normally we talk about compact set for the feasible domain, but this constraint is actually an open set, because you don't want 0. 0 will give you a trivial solution. You don't want 0. And you only care about getting this thing to be sparse. You don't care about the absolute scale. Okay? So the problem here is really how to fix the scale. I'm going to propose this simple way of fix the scale. I just fix the L2 norm to be 1, which is geometrically a sphere. Okay, so this is our problem. And just to make sense, when and how this kind of problem can be solved in a guaranteed manner, I'm going to put a little bit model on the data. I'm going to assume there's a ground truth orthogonal transformation Q0, which is fixed but unknown to us. And after you do this transformation, the coefficient is sparse. Okay, I'm going to assume these things on the data, Y. And again, this is our non-convex relaxation of our naive formulation of the problem. So this is a non-convex problem, and actually it's also a non-smooth problem, because L1 norm is not smooth at the point 0. But if you just pull out your MATLAB and write some simple code, say subgradient method, and try random initialization and see what happens, what you see is actually that just run these things many times, you have a pretty good chance of recovering the ground truth transformation. Okay, now this is a numerics, and I would say it's quite surprising if you try this. Yes?
Because that's an L1 norm. You got the sum of the absolute values. How does that make things 0?
This one?
Well, you want things to be 0 in
Yes.
the transformation, but that doesn't guarantee 0. That just guarantees that a sum is.
That doesn't guarantee 0, but over the past decades, people have been studying things like compressed sensing, this kind of thing. What they discover is that often under some mild conditions, it's a case that if you use L1 norm instead of L0, you exactly get the sparse thing you want. But these are under certain conditions. Okay. Yeah. But anyway, yeah, that's a good one. Okay. So we have this numerical surprise. So what happens here? Just to make some sense and just to inject some intuition here, let's look at a low-dimensional variant of the problem. Let's assume the dimension here is only 3, so that you can make some plot. Okay, this function is a function on the sphere. Now I assume the dimension is 3, so you can make a plot of the function on the sphere. Okay, and just to simplify the problem, I'm going to assume the ground truth transformation is actually identity. And also, this M is infinity. So M here is the number of measurements you have. It's the number of columns in Y. Okay? And this is what happens if you make your MATLAB plot. So 2 interesting things here. One interesting thing is that you have multiple local means. Okay? You have multiple local means. And actually, numerically, all of them carry the same function value. So all local means are global here. And also you have some kind of saddle point-like things. Okay, for example, this point, if you move along this direction, you have a concave curvature. If you move along this direction, you have a convex curvature. Okay, so 2 things. We have global means. We don't have spurious local means. And also we have a nice saddle point. Okay. Remember these 2 points. They are important later. So this is just a low-dimensional example. What happens in high dimension? Of course, we can't plot high-dimension functions. Okay. The only tool we have is do some analysis. And so what I do here is that basically I'm going to take derivatives, maybe even into higher order derivatives besides the first order, and I'm going to use the basic knowledge about the derivatives to make sense of the function. Okay, that's actually freshman calculus, right? Okay, but there's one problem. This guy is non-smooth, right? This one is non-smooth, so one way of dealing with that, I'm going to smoothen things out, okay? I'm going to take the red curve instead of original blue curve. The blue curve is the absolute value function. And the red curve is this complicated smooth function, okay? You may or may not like it, but you can choose other ones if you like. But anyway, just for analysis, I'm going to, I need to make sure the coefficient is sparse. I'm going to put a little bit of probability model on x0 so that it is sparse. In particular, I'm going to put a Bernoulli Gaussian model on the coefficient. So actually, the exact model doesn't matter, but the most important thing here is that you should have some way of control the sparsity level because you want some sparse matrix. Okay, so here the Bernoulli parameter theta will control the sparsity level. Okay, so what happens is that basically for these smooth functions, you take derivatives, you partition the domain into multiple pieces, you study the shape of the function in each piece, and then you piece together the function landscape. Okay, I'll skip all of these things. Okay, these are technical details. And also, remember that when I make this plot, I assume we have infinite number of samples. M is infinite when I make this plot. But in fact, we only have a finite number of samples in practice. So I'm going to show that qualitatively, even you have finite but sufficient number of samples, the landscape is going to be like the asymptotic variant. Okay, by some concentration argument. But anyway, these are technical details. So finally, what you can get is that when you have enough number of samples, even the sparsity level is linear. Okay, you can have a linear sparsity. Remember, theta will control the sparsity level in matrix X0. Okay, say we pick 1/3. Okay, then with high probability, all local means are global, which is nice, and all saddles are nice. Okay, I will actually clarify what is nice later. Okay. But the moral of the story is just that, when we have enough data, all of a sudden our, non-convex problem become tractable. Okay, that's the moral of the story, yes.
So why is sort of the data in this problem?
What is?
The variable y.
Oh, yeah.
The data?
Yes.
So are you making any assumptions about y for the result asymptotic?
Oh, yeah. We actually, yes. So the coefficient are Bernoulli Gaussian.
It's the y stuff.
Yes. And our y, remember our y is generated by, if Q0 transpose applied to y is equal to the coefficient. So we have some model. Can I put it here? Remember our model is a Q0 transpose y is going to be x0.
Oh,
Okay. Our Q0 is deterministic. It's an orthogonal matrix. And x0 is Bernoulli Gaussian, ID Bernoulli Gaussian. So we have this, and so why we bother, doing this non-convex analysis and non-convex optimization? So before this work, before our work, there are efficient algorithms that can solve the, sparsify and transform problem, but only when the coefficients are super sparse. So here, the sparsity level are sublinear in dimension. Okay, and also there are some inefficient algorithms that can actually solve up to linear sparsity level, but again they are inefficient. And by doing non-convex analysis and non-convex optimization, this is the first work that actually provide an efficient algorithm that can solve the problem up to linear sparsity level. Okay. So come back to our, central question: what kind of non-convex problem are easy? So just now I gave you one example. Okay. The example has this kind of characteristic global structure, so that property 1, all local means are global. Property 2, all saddle points are nice. And I'm sure you have some question why I emphasize all saddle points are nice. So if you think about saddle point, I think most people will think of saddle to be of this shape. Okay, they really look like a saddle that you can ride on. Okay, but by definition of saddle point, this point is also a saddle point. Okay, this is only a two-dimensional example. Imagine what happens in high dimensions. You can get crazy, non-saddle-like things. The reason that we distinguish between this kind of saddle and this kind of saddle is that computationally, this kind of saddle is hard. Computationally, it's hard. Okay, so we like this kind of saddle-like saddles. We call it nice saddles. Okay, we don't like these kind of saddles. So after we work out the dictionary learning problem, it turns out this phenomenon is not isolated. We can actually discover quite similar structure in different areas. Just to give you a brief example, another application cases, I will just highlight this Fourier phase retrieval problem. So the Fourier phase retrieval problem is basically given phaseless information of a signal, okay, you try to recover the signal. So basically, you do Fourier transformation on the signal, and then throw out the phase information, and then you want to recover the signal. For various reasons in applications, people would like to study this so-called generalized phase retrieval problem, where they allow arbitrary or generic measurement instead of just Fourier measurement. Okay, this is called a generalized phase retrieval. It actually found a lot of applications in imaging. And for this problem, it turns out under some generic assumptions on the measurement, and also provided you have enough measurement, a natural non-convex formulation for this problem also have the characteristic global structure that all local means are global and all saddles are nice. Okay, so this is an application from a totally different area. Yes?
Again, so are there assumptions about the A's?
Yes, your A's need to be generic. Say they can be Gaussian, or they can be Fourier times some mask. You kind of want your A's to be generic.
If the A's are just a strict Fourier transform,
Yeah.
does it work then?
Well, there'll be a long story. I'll actually come back to this later, but just bear with me now. Okay. Okay. So remember the characteristic structure. All local means are global, and all saddles are nice. And we worked out two examples. And after these two works, it turns out that people across different domains in computer science, machine learning, and even deep learning, people find applications and formulate their problem as non-convex problem, and they can work out similar structure across roughly over 10 examples. So this is really like a global, a kind of universal phenomenon that's not only tied to a single problem. And the good thing about this kind of structure is that once you can verify your problem has this kind of global structure, then virtually you can try any reasonable numerical optimization method. You can try gradient descent, you can try second order method, or whatever you like. You get a global solution. Another type of answer, that's answer one. Another type of answer is more like local. So for other problems, maybe you don't have this nice global structure. And what happens is that around the global mean, you are trying to seek locally the function landscape is nice. So the way to solve this kind of problem is that you initialize at some point that's near the global mean, and then you do some local refinement. There are actually far more applications in this line compared to the first category. If you are interested in both the problem with global structure or with local structure, you can check out my website on this topic on probable non-convex operation problems. It's updated weekly, so you get a most recent literature on the development. And you can also read the short survey paper I wrote, and also this more recent survey paper on these topics. So at this point, I want to pause for questions. Any question about this part? For these non-scary, smooth problems? You get exactly the sparse solution you want. Under some conditions. Under some conditions. Okay, so for all these examples we know, for all these either global or local ones, all the formulations are smooth, okay? And the way to study this kind of function is that I basically take out the derivatives, either first order or second order, and study what a function looks like by studying the derivatives or sometimes directional derivatives. A natural next question is, what about non-smooth, non-convex functions? Here, by non-smooth, I mean the function can be non-differentiable, even in first order. Just to give some idea that non-smooth problems are actually widespread. In optimization, people can use non-smooth penalties to study constraint optimization problem. They call it exact penalty method. And of course, in statistical estimation, when you want to promote robustness in your estimation, normally people tend to choose non-smooth functions. And if you also have nonlinearity in the process, you have non-smooth and non-convex problems. And also, over the last decades, whenever people want to promote structure, for example, sparsity, low rankness, they want to use, or they like to use non-smooth functions. For example, L1 norm or nuclear norm. And in neural network, people would like to use ReLU, which makes the problem non-smooth and non-convex. And there are a lot of other things. And a natural idea, which we actually did it just now, is why not just smoothing out the problem? Okay, it's very natural and it's very competitive idea actually. I would say there are two reasons at least. One reason is that if you want to solve large-scale optimization problem, it turns out often that by using non-smooth regulators, you can have some very specialized algorithm that can really scale up. For example, I think people have heard things like ADMM or coordinate descent, these things. It turns out they work well with non-smooth functions. Okay, this is a practical consideration. And for the theoretical consideration, I'll tell you a short story. So remember we smoothed out the L1 norm to get the result on specifying dictionary learnings or specifying transform learning. And it turns out by doing smoothing, we wrote a paper that's over 100 pages. Okay. The main culprit there is actually the smoothing. Okay, you think smoothing is going to smooth things out for you? That's not true. Okay, that's not true. We wrote an over 100-page paper and we submitted to this prestigious mathematical journal called Foundation of Computational Math. And we got immediately rejection within 1 week. Okay, the editor-in-chief wrote to us that, I think this is a very strong result. It's a nice result, but we haven't accepted any paper of this length in this journal. And you are not proving Riemann hypothesis, so I can't accept it. Okay. But anyway, my point is not to complain this journal. This journal is a very good one. Okay. My point is that if you want to smooth out, take some risk. Okay. So if we don't want to smooth out, what we can do? Can we just directly tackle the non-smooth problem? Especially if you want to study the geometry of the problem, what are the natural replacement for the derivatives, or even the second order, things? It turns out people in the area of optimal control and economics, they have worked out a pretty nice notation around this back into 70s, actually. Unfortunately, this set of tools is not quite common in the area of machine learning and data science. So the idea is to focus on a restricted class of functions called locally Lipschitz functions. So as the name suggests, locally Lipschitz functions are functions that are only Lipschitz locally. Okay. And actually most, I would say 99% of the function you would choose to work with are locally Lipschitz. Okay, it includes any continuous differentiable functions, any continuous convex functions, any continuous concave functions, and even strange ones like distance function to a set. Basically anything you can imagine, I would say. And also, manipulation of these kind of functions. They are all local ellipses. Once you have this, you have a notion of derivative, or technically speaking, we would like to call it subdifferential for these kind of functions. Okay. The reason you can have a nice notion is that once your function is local Lipschitz, it's actually true that your function is differentiable almost everywhere. Okay. Once you have this nice property, you can go ahead and define a notion of subdifferential by doing this. You basically take, at a point x, you basically take the neighboring point around this point. You take their gradient sequence limit. You collect this limit, and you take the convex call. Okay? So you take many convergent sequence to the point, and then you take the gradient limit, and then you take the convex call. That's the definition. And this thing was introduced by this guy called Frank Clark, who is a former PhD student of the convex analysis giant Rockefeller. And this set of tools, as I mentioned, is well known in optimal control and economics, but not quite in machine learning and data sciences. The nice thing about this kind of Clark subdifferential is that it's always non-empty, convex, and compact. Okay? And also you have almost everything you desire. Okay? So if your function is continuous differentiable, it's a normal derivative. If your function is convex, it's actually the Euro subdifferential you talk about in convex sense. And also you have nice calculus rules, and you have optimality conditions. Almost everything you want. So the answer to this question is that for the first order geometry, it's very natural to actually replace the derivatives by this Clark notion of subdifferential. And it's even possible to do second order geometry, but for the sake of time, I'll just escape this technicality. But bear in mind, it's possible to do it. Okay. So let's back to our troublesome specifying transform learning problem. And let's recall our 100-page papers. Okay. And so the problem here is can I just do direct non-smooth analysis and solve the non-smooth non-convex problem directly? It turns out that yes, you can actually use the Clark subdifferential notion, but here you actually have a constraint problem. It turns out you can actually generalize the notion to a constraint setting. I'll escape the details. But basically, everything you hope for would work out. You can actually show that, on the sphere, this non-smooth function actually work very nicely. Okay, and you can even design some very lightweight numerical method to solve the problem. Again, these are just the details. And finally, what we end up to have is that by doing this non-smooth analysis, we actually get some better result than the smooth version. Okay, of course you will say, okay, maybe you are not technically advanced, so you are doing suboptimal analysis. But anyway, I mean, we actually get better result. And just to compare, with works in the prior literature, especially I want to emphasize the comparison with the smooth one. So by doing this non-smooth analysis and non-smooth optimization, we actually managed to get stronger result by compressing the proof by a factor of half. So now you basically get a stronger result within 40 pages, something like 40 pages. Okay. But I'm not saying this is a big factor or the point I want to make here is that actually it turns out this is the first time in the area of machine learning and data science people put together this nice set of tools, okay? And this set of tools turns out to be highly non-conventional, but accessible, actually. So just to give some idea about the technicality around the analysis, as I mentioned that the subdifferentials are going to be set. Okay, they are going to be convex set. You need to measure distance between set. Okay, you have some nice notion of that. The more troublesome part is that you have some randomness assumption in the data. Remember, we have some assumption on y, right? And we have some probability model on the coefficient that influence y. So you have set, and you have some randomness. You actually have some random set. And the analysis proceeds like, I want to argue that typically this random set is behaving nicely. By typically, I mean I need a notion of expectation of random set. And after that, I need to argue that with finite amount of data, the set actually behaves like the typical set. That means I need certain notion of convergence or concentration, if you like. So I need to set expectation, I need to set concentration. And as I said, these tools are not quite conventional in machine learning and data science. And this is the first time we actually successfully put these things together. And I believe that these things can actually be used to solve quite a number of other non-smooth, non-convex problems. So for the sake of time, I'll ignore this interesting discussion about the current state of affair around non-smoothness. If you're interested, you can talk to me offline. So far, I've been talking about taming non-convexity. So I think by taming non-convexity, first of all, you need to live with non-convexity. Because as I said, most problems that you will encounter are non-convex, and often it's hard to try to convexify the problem. And you need to live with these things, and you need to understand these things. Because if you understand these things, you can actually use the insight to solve other practical problems. So as for the first question, which kind of non-convex problem are easy? I highlighted the first kind of answer, where it basically says, there are problems where we have enough data, and if the data are generic enough, this is particularly relevant for the modern data science problems. Then you tend to have some nice global structure for the non-convex problem you have. Sometimes maybe you are not that lucky, you don't have the global structure, but you may have some local structures you have, okay? But the problem about the second kind of thing is that you need some initialization, and doing initialization for a non-convex problem is a tricky thing. And what about non-smooth, non-convex problems? Well, it seems to me that we are still learning the right language. So actually, some people tend to smooth out the problems they have, or some other people tend to just ignore the non-smoothness and just assume they can do smooth calculus, which is basically wrong, I would say. Okay. So what I have done is that I basically put together this set of non-conventional but acceptable tools from non-smooth analysis and the random set theory that hopefully can be used to solve quite a number of practical problems in applications. So this is the second part. Any questions on the non-smooth part? So in the last 10 minutes also, I would like to briefly mention two other things. That's also in the line of taming nonconvexity, but you see that they are actually in quite different spirit of dealing with the problem. Okay. So for some problem, taming nonconvexity means you have to rethink the formulation you have. It's not the case that the natural one you would write down is the one you would successfully solve. Sometimes you need to tweak your formulation a little bit. Just to give you some concrete example, I would like to mention this sparse blind deconvolution problem. So this problem looks a lot like the dictionary learning problem I mentioned at the very start. Okay, you have kind of factorization problem. Given data y, you want to do this factorization. But the difference is that here, you have convolution between this part and this part. Okay? They are not like the simple matrix modification. They are convolution here. Why we care about this problem? Again, you have a lot of applications around image processing, around actually neuroscience. And I would especially highlight this application in microscopic analysis, where the reason you have this kind of structure is this. Okay? So in this set of application, physicists want to study why superconducting material can be superconducting. Okay? They kind of conjecture that the reason they can be superconducting is that there are some basic signature in the material that cause the physical phenomenon. And one way of modeling this physical process is that, okay, I hope I use the board. Imagine that we have some basic structure, basic signature, and then you have a material, superconducting material. And for physical reasons, you somehow have this basic signature scattered around the material. Okay? So one way of modeling this process is that this is our data matrix Y. I'm going to write this Y as convolution of this basic structure and the sparse support map. Okay? The support map is going to be center of the stars. Okay? So we have this A0 to be the basic signature of interest, and X0 to be the support map, which is sparse. So I think in terms of formulation, it's quite natural, whenever you have this kind of problem, I want to penalize the approximation error in this factorization. And I want to promote sparsity. As I said, the support map is going to be sparse. But the problem is this. Obviously, you have some scaling problem here. For this formulation, I can always scale up A and accordingly scale down X. I get same value for this term. I get smaller value for this term. So the solution is going to be X has to be 0 ultimately, which we don't want, right? So the problem is, how do we fix this scale problem? In other words, what kind of constraint you want to put for this scaling problem? In another application in computer vision or image processing called image deblurring, people tend to put this constraint called simplex constraint. The reason people like this constraint is that in image processing, it's often the case where you're seeing your kernel interests are non-negative. So I would like to put a non-negative constraint there. And also I want to fix the scale. And it turns out the thing work well with the non-negative constraint is actually this summation to 1 constraint, which makes this whole thing to be a convex set, which is called simplex constraint. Okay. So people have practiced this a lot in image processing, but unfortunately, it's well known that you actually have some trivial solution for this formulation. Okay. What people are doing in computer vision is that, okay, maybe I just try multiple initialization, and when I'm lucky, maybe I get something meaningful instead of this trivial solution. But we know for sure that the trivial solution is there. Okay. But if you were just to make a slight change to a formulation, remember for our specifying transform learning problem, we put spherical constraint instead of other constraints. If you just replace this constraint by a kind of spherical constraint, so here F is a Frobenius norm because A is a matrix. It turns out all of a sudden you actually get some nice global structure. Okay. You can show that all local means for this formulation, inserting this spherical constraint here, all the local means are relevant to the thing you want to recover. Okay. And numerically, it's working remarkably better than other approaches for the image deblurring problem, and also for the microscopy analysis problem. Okay. So the moral of the story is that sometimes you do need to tweak the problem formulation a little bit. I'm not saying that any formulation, any non-convex formulation you write down has some nice global structure. That's not true. Okay. And sometimes you even want to modify the physical system that's generating your data in order to make the problem well posed or well solvable. And we come back to this physical problem. That was actually a very good question. So people have studied the generalized physical over the past, I think, 9 years. So the fortunate thing is that people have used, that non-convex formulation to gather a lot of mathematical results that actually inspire further development in solving non-convex problems. That's the good part. Okay. The bad part that people don't want to tell is that actually the algorithm that's inspired by that kind of analysis doesn't work with real data. If you have Fourier physical problem, you can run gradient descent, you can run second order things. It won't work. Okay, that's a very unfortunate thing. So what happens in practice is that practitioners in imaging basically use this so-called hybrid input-output method, which is basically an advanced version of alternating projection between non-convex sets. And this method was invented back to, I think, late 70s. It's been used for more than 4 decades. Nothing has ever beaten this method, as far as I know. But there are also a lot of complaints. People complain that often it's slow in practice, and also there's no guarantee that the method will work because you are doing alternating projection onto non-convex set, which is tricky. It turns out you can actually do a slight modification to the system, especially for certain application of phase retrieval. So this one is called coherent diffraction imaging, which is basically the physical process of putting your sample here, inject some parallel light on the sample, and then due to the physical diffraction, you collect a diffraction pattern at a far field. Okay. This is used to image a small scale object. So the trick here is that you can actually put a small known reference to the system. This is physically feasible. Actually, we fabricate with Slack at Stanford. This is quite feasible physically. You put a small known reference next to the smiling face. Okay, you want to image. And all of a sudden, it turns out by doing this, your problem becomes the matter of solving a linear system. Okay, which of course you have theoretical guarantees, and you can even do more, fancy things like you have multiple reference. You can design multiple reference to make the system more robust, because in practical imaging you do have things like short noise, which is Poisson noise. Okay, you want to make the system to be robust. So by doing a small modification to a system, you can actually get robust performance and a very attractive running time. Okay, so this is another thing you can do around nonconvexity. Okay, so the last 2 minutes, just a very brief overview of my research and outlook in research. So I basically pick research problem in this set: machine learning, data science, optimization, computer vision, imaging processing, imaging. It's growing, okay. And over the past years, I have been focused especially on two central problems in foundation of machine learning and data science. One is representation learning, which is about learning efficient representation for your data. Our sparsify and transform learning is a good example there. The other one is non-convex optimization. Basically, I care about when and how non-convex problems, maybe also non-smooth, can be solved in a guaranteed manner. And basically, over the years, I pick project in this product space of representation learning and non-convex optimization. I have derived efficient representation for doing video analysis, actually, although I haven't talked about it in this talk. And also, I have analyzed, when you can actually model hybrid data from multiple sources in a provable manner. Of course, we talk about diction learning or the sparsify and transform learning. And also, recently, I'm more on the signal processing and the imaging side, where I care about, how to do face retrieval practically and probably. And also, we talk about blind deconvolution. And deep learning, I would say, is right on the diagonal of this product space. And that's definitely within my agenda, to understand the deep learning in the next few years, and also use the insight to solve practical problems in, these application areas. So these are the possible future